Hello, I'm Martin Thijsens, and on behalf of TAS International, I welcome you to the MADYMO Introduction training on material models. The material models in MADYMO cover material behavior starting from as simple as rigid material or no material for holes to linear elastic, elastoplastic material, foam material, or even fabrics and more complicated material. Here we'll give some details on the basic material models needed for some finite element calculations. Let's start with the material.isolin, which represents an isotropic linear elastic material and is characterized by a Young's modulus of elasticity E, a Poisson's ratio nu, and a density rho. The material model also comes with damage, isotropic damage, and in airbag analysis can be used as with the options tension only, a heat transfer coefficient, and permeability models. The next material model is the rigid material model, which is basically only characterized by a density rho, and for contact interaction, in this case for penalty contact, a Young's modulus E and Poisson's ratio nu, which are only used for the contact calculation. The null material is generally used for the MADYMO facet occupant models and is characterized by a density rho, but also by a Young's modulus E in case of penalty contact, and similarly the Poisson's ratio nu, and can be optionally given a contact characteristic for characteristic contact. The next material model is the His-Iso material, which represents an elastic material with hysteresis. Besides the density rho, the material is fully characterized by a loading and unloading stress-strain function, an elastic limit, and a hysteresis slope. This material model does not allow for lateral contraction, that is, the Poisson's ratio is per definition 0. Also, this model is often used in airbag and belt analysis and comes with tension-only parameter, damping, rate dependency, a heat transfer coefficient, and permeability models. The foam material in MADYMO is similar to the His-Iso material, characterized by a density rho and by a loading and unloading stress-strain functions, as well as a hysteresis slope and elastic limit. Again, the Poisson's ratio is 0, but in this case, stresses are calculated in principal strain directions. The stress-strain definitions specified for the loading and unloading curve are either given as true stresses versus logarithmic strains, or nominal, the engineering stresses versus engineering strains. Furthermore, only hysteresis models 1 and 2 can be used for this material. Just a very brief recap of engineering and non-engineering and logarithmic Cauchy stresses is given here, where the engineering strain is the deformation divided by the original length, and logarithmic strains are defined by the current length divided by the original length, and then the natural logarithm out of that. This translates into how a stress-strain curve is defined for this material. For example, on the left side you see a curve in engineering units, and on the right side you see the same curve in terms of Cauchy stresses and logarithmic strains. Finally, material damping can be added to a material model with a damping parameter and can be chosen to be either element size dependent or element size independent. Note that adding damping to a material model makes the critical time step become a little bit smaller. Adding damping, typically a few percentages, is strongly recommended to make sure that high frequency vibrations in finite elements are damped out sufficiently and that the calculations remain stable. This covers the introduction to the material models. Thank you very much for your attention.